Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We have been discussing on some of the applications of stable water isotopes in different reservoir, and we are discussing the oceans in this particular lecture. So, in our previous lecture we were discussing how the oxygen isotopes will vary in the oceans with changes in evaporation, with changes with respect to precipitation, with changes with respect to addition of fresh water coming from ice melt water, and also due to the formation of sea ice. So, when the Arctic is forming, so it is the ocean mass itself that is getting frozen to form the ice. So, that kind of freezing, okay, what will happen? The salinity will rapidly increase as compared to the delta 18. So, therefore, we see such shallow changes with respect to delta 18, but much rapid change with respect to salinity. Okay. And that is because of the difference in the del means the del factor, del value of 18O with the sea ice, that means the sea ice that is forming and the water itself. Okay. So, now let us look into some of the salinity and delta 18O values. So, as you can see here that different sea masses, the data from different sea masses has been plotted, okay. And let me just tell you that this is the surface water, this is not the deep ocean water, this is the surface water and changes with respect to salinity. Because in the deep ocean the salinity difference is also very muted and the delta 18O value also gets muted. So, this kind of delta 18O relationship where there is a lot of variability we are observing, but we are observing it in the surface water of the ocean. That means a few hundreds of meters into the ocean. Okay. So, this is a plot that can show you, the variety of ocean masses. So, here we have the North Atlantic surface water, we have the Central South Pacific, we have the Equatorial Atlantic, we have the North Atlantic deep water, Pacific and Indian deep water, Antarctic bottom water, Weddell Sea. Weddell Sea is something near the Antarctic. Okay. So, there is a Weddell Sea. So, all the data is plotted, and what we can see is that there is a very good correlation with the salinity. Okay. So, with salinity and delta 18O there is a very strong correlation, and this is extremely helpful because how salinity has changed in the past. Okay. If we get information on that, then if we can infer about the delta 18O values. So, there is an empirical relationship, that is delta 18 oxygen is equal to 0.45 times the salinity minus 15.5. Okay. So, this comes from a lot of data from different oceans, okay, and it has been really helpful to understand how it is varying in the different regions and in the past. But in the tropics we observe a little slight difference. So, here as you can see that the slope with the salinity is 0.45, but in the tropical region where we have again data from different areas, we see that the slope is much shallower. Here the slope is very shallow and its value is around 0.273 in the deep tropics, that means between 0 to 5 degree north and 5 degree south. Okay. So, it is just the equator 5 degree north and 5 degree south. In this particular region we have these very shallow changes in delta 18O and salinity, but it is 0.45 everywhere else. Okay. So, this is the two empirical relationships that we have seen with the surface water and salinity in the ocean. Now, it is also useful to know what are the signatures of the different oceans. Okay. So, here we have the North Atlantic deep water, whose salinity, as you can see, is this 34.93, and delta 18O value is plus 0.12 parts per mil. Okay. The Antarctic bottom water is slightly negative. So, it is slightly more negative, minus 0.45, and it is remembered that this is a very again cold region of the planet. So, it is Antarctic bottom waters. Then there is Indian deep water. So, the Indian Ocean, not the surface water, but the deep ocean, that is something around minus 0.18. The Pacific deep waters is something around minus 0.17, and near the Antarctic the values can go to the minus 0.21. So, this Antarctic samples means the Pacific Ocean only, but close to the Antarctic region, that can have slightly more negative values of minus 0.21. Now, this kind of values, okay, this kind of variations, this kind of small variations also can be extremely useful in understanding how the different ocean masses are mixing, they are forming the currents, where there is upwelling going on, where there is downwelling going on, we can find out. Okay. So, as you can see that although the isotope compositions and salinities, okay, of the surface water. So, surface waters, that is up to a depth of 1 kilometer, the total variation, okay, in the isotopic composition of the deep ocean water is only 0.3 parts per mil. Okay. At a depth of below a depth of 1 kilometer, the total variation in the isotopic composition of deep ocean is only 0.3 parts per mil. The maximum variation we see is in the surface water. Okay. It is in the surface water, and as you can see, it varies considerably with the latitude. So, whether it is a North Atlantic, whether it is a Indian Ocean, whether it is a Pacific Ocean, okay, it varies a lot with the latitude. And when we plot the data, so here is a plot of the salinity with the delta 18O value, and here we plot the surface ocean water. So, here plots all the major North Atlantic, North Atlantic ocean masses. Okay. So, here it shows that the NAW, it says the NAW directly plots on top of this line, which is like a mixing of different waters. So, here we have the Greenland east coast, so a mix of this end member, and we also have the Norwegian Sea, the Bermuda area, so that region. Okay. So, mixing of these two waters forms the North Atlantic deep water. Okay. Now, this North Atlantic deep water is a downwelling, it is a downwelling current, it is a cold downwelling current. Okay. So, independently there are certain circulation models which works on basically physical constraints, and where the density should be changing such that there is a downwelling happening. But from our geochemistry data as well, we get supporting evidence of such kind of mixing, where we see that different ocean masses, if this is considered A, this is considered B, then these kind of mixing can give rise to my downwelling current, such as the North Atlantic deep water current. Okay. So, this kind of understanding becomes very, very important. Now, this just to mention, this is Greenland ice sheet data. So, this is very, very close to the Greenland coast. This is not ocean water, itself, it is basically reflecting the ice melt water. So, just do not get confused with the ocean. The ocean is not very negative, but the ice melt water near to the estuaries and near to the coast is extremely dominated. When it is very dominated with the fresh water itself, that time it can have the signature of the entirely, which is the signature which is entirely terrestrial. So, therefore, such negative value. And you can see that in the salinity itself, where the salinity is very low. So, it reflects the, you know, that this water is very close to some kind of you know, melt water discharge, very close to the ocean, such that it is in the mixing zone of fresh water and a marine water. So, this is another example that shows us how delta 18O value and salinity value can help us understand the mixing and formation of different ocean masses. For instance, here you see this is the North Atlantic deep water, okay, and this is the data of the Antarctic bottom water. The double A is always for Antarctic. When it is for Arctic, it is single A. When it is for Antarctic, it is always double A. So, in the when we are seeing the Antarctic, we see that there is a variation which is mostly along the salinity axis, right. So, that kind of change is because of the constant freezing that is happening in the polar regions. Okay. So, this again is the Pacific and the Indian deep water, okay, the Indian Ocean deep water and the Pacific Ocean deep water, and it is said that it is a mixing between these two ocean masses that is forming the Pacific and the Indian Ocean deep water. And you can of course see it in the data itself that the Pacific and the Indian Ocean deep water lies in between the Antarctic bottom water and the North Atlantic deep water. So, it is the mixing of this North Atlantic deep water and the Antarctic you know, bottom water that is forming the Indian Ocean deep water and the Pacific Ocean deep water. Okay. So, such examples of you know, delta 18O is very useful in understanding how the ocean circulation is working, how the air, how the ocean masses are getting formed in the different regions. Now, another extremely important factor that we always try to also you know, understand is how carbon, you know, how carbon composition, how our oceans has you know, how the oceans, how the carbon dioxide content of the ocean could have varied. Okay. Now, carbon dioxide you know, when we are using the carbonates also as a proxy, because often as I said that we have two kinds of samples, we can either use the delta 18O values of the water itself or we can use the delta 18O value of the carbonate. Okay. So, the carbonate are also a very useful reservoir, and along with the delta 18O data, delta 13C data is also very useful, and specifically since carbonate is a reservoir, delta 13C use you know, using delta 13C becomes very relevant. Okay. Now, the thing about 13C is that we know that you know, carbon, there are 3 isotopes, one is 13C, one is 12C and one is 14C. Okay. Among that 12C is the most abundant isotope, 13C is a little rare, and this 14 carbon is the cosmological nuclide, right. It is produced due to cosmic radiation interaction and it is continuously being produced due to the interaction of the cosmic rays in the atmosphere. Okay. Now, the majority of the carbon is therefore 13 carbon and 12 carbon in the ocean. Okay. Now, when biomass is uptaking carbon, it always prefers the 12 carbon. Okay. It is basically preferring the 12 carbon when we are trying to build the cells, any kind of biomass is getting built up. So, the organic matter is basically 13C depleted. It is like the formation of ice mass. So, when we are forming ice mass, it is 16 oxygen enriched, 18 oxygen depleted. Similarly, biomass is 12 carbon enriched and 13 carbon depleted. So, what happens is when that organic matter dies and decays, the carbon dioxide that gets produced from the decay of that organic matter also is 12 carbon enriched, okay, because this carbon dioxide is coming from that organic matter, right. So, therefore, this carbon dioxide is isotopically lighter. It is having more and more negative 13, it is depleted in 13 carbon. Now, we can use delta 18O values. We also have, when we are using delta 18O values, we also have to understand that there are some other processes in which delta 18O can also get changed, and one of that is the consumption of oxygen during the breakdown of organic matter. That is, when organic matter gets oxidized, dissolved oxygen also gets consumed. Okay. So, during that consumption, the lighter oxygen is always preferentially consumed. What will that mean? That will mean that if wherever there is more and more organic matter breakdown, my delta 18O value will get more and more positive in the ocean, because my 16 oxygen is getting consumed due to that oxidation of organic matter. So, due to that oxidation of organic matter, my delta 18O of the ocean will get increased. So, if you are looking into a profile, if I am looking into an oceanic profile, so from 0 kilometer to 5 kilometer, here there are 4 vertical lines. Let us understand what the lines are first. Okay. So, you will see there are 4 axes, one is the delta 13C, one is the delta 18O, here we have the oxygen and here we have the carbon dioxide. Okay. So, we have a region somewhere near to 1 kilometer which we call the O2 depleted region, that is the oxygen minimum strata. Okay. So, it is called the oxygen minimum oxygen zone. Okay. And why is this oxygen? So, as you can see in this particular plot, so O2 which is at equilibrium with the atmosphere, it slowly decreases and decreases very much in this particular region, it becomes a minimum value, and then after that it gradually increases and after a certain point it remains stable. Okay. It goes on remaining stables. Okay. Let us see how the CO2 value changes. So, the CO2 value starts here near the which is in contact with the atmosphere. So, this is very low and then it gradually increases, it goes on increasing up to this O2 minimum zone, after which it gets stabilized, okay, after which it no longer shows any significant changes and it remains almost constant. Okay. Now, let us compare that with the isotope value. So, we have here the delta 13C value and the delta 18O value. So, let us see the process. So, what is happening here? Here organic matter is getting broken down here. So, in this region our organic matter, so whatever so up to the first 200 meters we have the photic zone, that means which region the the layer of the ocean up to which sunlight can enter. So, up to the first 200 meters there is a lot of primary producers, secondary producers. So, a lot of cyanobacteria and all that is there. So, they are going on producing oxygen, and there is also a lot of animals as well. So, a lot of life is limited to the first 200 meters. Okay. A lot of life gets limited in the first few hundred meters of the ocean. As the depth increases, suddenly there is no more primary producers left, and the oxygen no more being produced also starts falling. Okay. So, the oxygen slowly first increases, but then starts falling. Okay. Here, because all the organisms that is living in this top surface, when it is dying, it is slowly falling, it is just making its descent into the ocean. So, it is slowly falling down, and while it is falling down, it can get eaten by other animals, or it just simply decays naturally. So, in this region there is a lot of decaying activity going on. Okay, there is a lot of decaying activity going on. Due to the decaying activity, due to large biomass that is getting oxidized, okay, due to the decaying and oxygen requirement of breakdown of organic matter, oxygen gradually and gets lowered, it gets less and less. So, there is a sharp fall in oxygen concentration. Okay. And as said that this consumption of dissolved oxygen to oxidize the organic matter and release carbon dioxide, preferentially 16 oxygen gets consumed, okay, because all these decaying bacteria, they are also using 16 oxygen, they use. So, biota always prefers the lighter oxygens, always the lighter oxygen and always the lighter carbon. Okay. It will always prefer the lighter oxygen and the lighter carbon. So, even those which are using oxidizing the organic matter, they are also preferentially using the oxygen, the 16 oxygen, to convert the biomass into some useful compounds for themselves and releasing carbon dioxide. Okay. So, carbon dioxide gets released. So, therefore, here the carbon dioxide is at its highest concentration. When the oxygen is at its lowest concentration, my carbon dioxide is at its highest concentration. Okay. So, here my delta 18O value is gradually increasing because my 16 oxygen is going into consumption, and what is getting produced is my 13 carbon is getting produced. Okay. Now, this 13 carbon is coming from the oxidation of organic matter. This organic matter is already 13 carbon depleted, it is depleted in 13 carbon. So, the carbon dioxide that gets produced is also 13 carbon depleted. Okay. So, if my atmospheric carbon dioxide delta 13C value is this, the new carbon dioxide that is getting produced from the decaying of organic matter has a value that is much isotopically lighter, that means depleted in 13 carbon with respect to the 12 carbon value. Okay. So, my delta 13C value goes on decreasing, and after this level it again increases and remains stable. Okay. So, below this layer, the delta the summation of the carbon dioxide also goes on remaining stable, the oxygen concentration also remains fairly stable, and the delta 18O and the delta 13C also remain stable. It is this huge organic decaying of organic matter flux that controls the changes observed at this particular level, at this particular zone in the ocean. Okay. And we have some empirical relationships, and when we are using samples, and we know at which zone this particular species likes to live, at which zone it is have, if the data shows anything odd, we can always go back and see, okay, why is it suddenly increasing, why is it suddenly showing these kind of changes. Now, what is the isotope composition of the ancient ocean? That was our question, right. So, the main questions that we are going to ask is, how frequently and by how much has the isotopic composition of the global ocean changed with time? Okay, how frequently has this changed with time, and how much? Okay, is it 1 parts per mil, 5 parts per mil, how much is that? Why does the present day sea water have the isotope composition that it does? That is our second most important question, that okay, if we know that in the past there has been difference, we expect that there is 0 parts per mil, but we see that there is either very negative values, minus 15 parts per mil, or some other data that we have got. What kind of processes leads to the formation of the composition that we see today, that is 0 parts per mil? What exchange mechanisms or what other buffering processes exist in the oceans that will cause the ratio to remain the same? Okay. Of course, just like any reaction, whenever there is happening, it is always not like it is very straightforward, it can have some kind of buffering as well. So, what kind of buffering capacity exists in the oceans? Okay. So, these are our 3 very important questions that is asked when we try to understand the delta isotopic composition of the ancient oceans. Now, from the mass balance studies and from the primitive oceans, from data from very old rock samples and all that, and basically from a lot of theoretical calculations, we have found that the primitive oceans would have been having a delta 18O value something around 7 plus minus 1 parts per mil, and the delta D value of minus 60 plus minus 20 parts per mil. Okay. So, what is that process that is causing the change from 7 parts per mil to the current value of 0 parts per mil? So, there are some hypothetical changes. The first is, okay, if there is escape of the lighter isotopes, okay, if there is an escape of the lighter isotopes, what will happen? If there is an escape of the lighter isotopes, then the delta D value will only change, the delta 18O values will not change significantly, or if it changes, then the water will again come back. So, that is only will explain a small change in the hydrogen isotopes. Second of all, which is very important, is the interaction between the ocean water and the hot basalt. So, within the ocean mass itself, so if this is my ocean and this is my oceanic floor, now this oceanic floor is it's forming and it is getting destroyed, it's again forming, it's getting destroyed. So, the oceanic crust okay, that is continuously interacting with the water. Okay. All the tectonic activities that is happening, all the hydrothermal events that is happening, all the formation of tectonic plates, eating or destruction of the tectonic plates. So, all that is happening in the oceanic system, and that is a very high temperature alteration. Okay. That is because it is the molten magma that is interacting with the water. So, there is a lot of high temperature alterations that is happening. What do we imply from the high temperature alterations? What kind of expectations do we have from high temperature alterations? So, there is a second possibility. Third possibility is the weathering of the igneous rocks or the clay minerals that is coming from the continents itself. So, there is a lot of rivers and all that is bringing in all these continents, terrestrial weathered products. How that interacts with the water, how that interacts with the ocean water, and if it can change. It is found that the delta 18O can change with such low temperature alterations is going on, if such weathering activities is going on. That is a huge implication where it can change from 7 parts per mil to 0 parts per mil. Okay. That is because 18 oxygen always prefers the stable phase, it always prefers the more stable, more strong phases. So, 18 oxygen will go into the clay mineral, because clay minerals are the weathered products. Okay. The igneous rock, other kind of rocks, they will weather to form the clay minerals, right. So, when during the formation of the clay mineral, 18 oxygen from the water will get incorporated in these hydrous clay minerals or the marine sediments, whatever is getting formed. So, that will trap the 18 oxygen. Okay. That is a major process in which 18 oxygen can get removed from the ocean mass. Here is a picture, here is an image showing a ophiolite. Okay. So, this is an ophiolite. Okay. What is an ophiolite? An ophiolite is a stratigraphic, it is a stratigraphic structure, and it shows the oceanic crust. Okay. So, in this oceanic crust, the bottommost layer is called the layered cumulate gabbro. Yeah. It is called the layered cumulate gabbro. Above the layered gabbro is the high level gabbro, and above that we have some pillow basalts. And this particular ophiolites has a diabase dike complex. So, dikes are so some kind of fractures and all that is there from where the magma can get enter. Okay. And its diabase a kind of composition. So, how much silicic, how much so it is like a rock type. So, diabase is called basically a rock type, just like gabbro is a particular rock type, okay, or basalt is a particular rock type. So, it is a diabase dike complex. Okay. So, this structure is called a dike. Okay. This shaded area is called the dike, and it is mostly from the entry of the magma, which is formed much later after this gabbro and all that the structure was formed. Okay. So, it is due to some fracture, and this fracture got filled up with the magma. So, it is having this kind of structure. Okay. Now, what is shown here is the delta 18O of the whole rock, of the entire rock. So, it is the rock delta 18O value. So, when the gabbro is getting formed, this is the high temperature, this is that particular region of the crust where it is in contact, this is the lowermost level of the oceanic crust. Okay. So, this is the very hot region. Okay. So, this temperature will be very, very high. What we see is during high temperature alterations, the hydrous minerals are formed less. Okay. And the difference between the delta 18O of the rock here and the water is also low. Okay. So, the water and the rock does not exchange or is basically having equilibrium exchange of the 18 oxygen. So, there is not much difference between the basalt and the water. Okay. So, if there is high temperature alteration, the 18 oxygen is not getting preferentially incorporated in these rock types. But what we see is that as we are moving up, as we are moving towards the higher topper surfaces of the rock, we are seeing that this region has more heavier isotope data. It has more heavier isotope data. What does this mean? This means that here whatever alterations are happening, whatever clay minerals, whatever low temperature alterations are happening, here the 18 oxygen is preferentially getting stored inside the clay minerals, it is getting trapped. That means the water is losing its 18 oxygen to these minerals. So, the oxygen is getting depleted in the ocean and enriched in these minerals here. So, therefore, the ocean will start getting more and more negative 18 oxygen, delta 18 oxygen composition. So, its isotope composition will start falling. So, when we start to question that okay, what kind of buffering processes are happening, what kind of compositions we expect. So, we say that the processes that affect the 18 oxygen and 16 oxygen ratio of seawater is, first of all, the continental weathering. Continental weathering lowers the delta 18 of the ocean. Why? Because of the low temperature alterations, because this continental weathering is supplying more weathered products. It is supplying weathered products, and these weathered products is finally going to form the clay minerals. The final fate of these weathered products is clay minerals. Clay minerals has more 18 oxygen composition. So, the delta 18 of the ocean will gradually get lowered, and any other kind of low temperature alteration will also favor the delta 18O moving from the water phase to a more stable phase, that is in the rock phase. Okay. So, therefore, any other low temperature alteration is also going to lower the delta 18O value. In the high temperature alteration, that will probably raise, either it will not change or it will raise the delta 18O value of the ocean, because now these rocks, as you have seen in the geothermal exchange, these rocks are rich in 18 oxygen and they are going to supply these 18 oxygen to the water. So, high temperature alterations or geothermal alterations, they are going to raise the 18 oxygen of the ocean. Okay. Water recycling, that is associated with subduction and magmatism, it's basically depends on whatever is happening. So, it can either raise or lower the isotopic composition. Then glaciation, how will glaciation affect? So, glaciation again is a huge phenomena. So, the delta 18 of seawater is going to get heavy as glaciation is happening, because all the 16 oxygen is getting trapped in the continents, and the seawater delta 18 is getting more and more enriched. So, it is going to get heavy by 1 to 2 parts per mil, and if glaciation is happening in a few hundred years, then it can happen within a very short time scale of 1000 years when we are looking into the long time scales. So, glaciation, weathering, formation of new oceanic crust, hydrothermal alterations, all these kind of processes is going to impact the ocean water delta 18O values. But to happen, to change something to a very significant degree, it has to be a very significant event. The event has to be either significantly long or huge in terms of its volume, because the volume of oxygen and hydrogen isotopes is huge in the oceanic reservoir. So, with this I come to the end of the discussion of stable water isotope applications in oceanic system and with other aquatic systems as well. In our next lecture, we are going to start looking into another isotope system.